Hi, today we're going to talk about something which confuses physics students quite a lot, and rightly so. Why? We're going to talk about electromotive force and voltage. And the thing that most confuses students is that electromotive force, even though it's called a force, it's not a force. So, EMF, which is electromotive force, is really energy. First thing that is strange, it's force, it's called force, but it's really energy. Secondly, it's energy measured in volts. What? Okay, yes. Why is it measured in volts? Because there's a direct relationship between volts and energy, and is that 1 volt, 1 volt equals 1 joule per coulomb. That is, if you have a battery of 8 volts, it can transfer 8 joules per coulomb, per unit of charge. Okay, so EMF is energy measured in volts. It's not a force, and that's the first thing that confuses students. Okay, so what does it represent? Well, imagine one of those cells that you have, or batteries that you have at home, and you've got the positive electrode and the negative electrode. Okay, and you know that if you connect something here, uh, in electricity, we talk about the current going from the positive to the negative, but we've already seen in that's the conventional current. The real current, how the electrons move, is not the other way around. Electrons move from the negative electrode to the positive one. Okay, so they move. So if you've got an electron here, it moves to the other side. Okay, perfect. And then it has to go through the battery, and the battery has some sort of liquid or gel that produces chemical reactions. Okay, so that, through that chemical reactions, uh, the electrons are transferred from one electrode to the other. Okay, to do that, the battery needs to provide through those chemical reactions energy, and that energy is the electromotive force, again measured in volts. So it can provide, for example, 8 volts per charge. Okay, so that's the energy that it need that's the electromotive force, the energy that the battery is providing to move electrons from one electrode to the other. Okay, and if life were ideal, in ideal cases, the electromotive force would equal the potential difference in both sides of the battery. Okay, so that would be the same. However, life is not ideal, and really we know that when we're trying to move something through a liquid or a gel, we will have we will lose energy either in those chemical reactions, in resistance, in the form of heat or whatever. So if the battery is providing 9 volts, we will probably lose, imagine, 2 volts. Okay, so in the end, the battery is providing 7 the battery is the effective voltage in the battery is 7 volts. Okay, so this is the loss in whatever kind of energy. Okay, so this loss, this final voltage, is what we call the potential difference of the battery. Okay, so in the real case, the potential the energy from the battery minus the whatever is lost here in inside the battery, which we normally represent as another voltage. Okay, we'll call it voltage lost, or voltage of an internal resistance. Okay, that would be the potential difference of the battery. We already know Ohm's law. Ohm's law is that. So if we can represent the loss of the battery as if it had an internal resistance R. Okay, so really we can change that formula into the ideal potential difference that the battery would provide, the EMF minus the intensity going through the battery times an resistance which represents that loss in energy, that would be the potential difference of the battery. Okay, so that's the famous formula that we have for EMF and voltage. Okay, so when we're doing exercises, we will normally have here your cell. Okay, that's not normally represented. I'm doing it here so that you can see the cell is represented like that, and we will have either in front or at the start or at the end of the battery, we will have here this term of the internal resistance, which is normally represented as a lowercase r. And then we can connect something there, okay? Yes. So the battery would be providing really our EMF in volts, but we are having some energy lost there in that internal resistance that again represents all the processes that are wasting energy inside the battery. Okay, so if we were to do this, and that would effectively at the if we measure the potential difference of the battery, we would have, as we have already seen, the ideal quantity minus the losses. Okay. And if we have a resistance here, R, as it's connected directly to the battery, well, the potential difference would be I times R. So we would have, okay. And we could calculate knowing the EMF, we could and the resistance, we could calculate the internal resistance or whatever. So to summarize this, EMF is the theoretical energy that the battery can provide. Energy in volts because it's joules per coulomb. Okay. Life is not so perfect, so there's internal loss that we represent as an internal resistance. So I times lowercase r normally is that loss in voltage, and the potential difference of the battery is the EMF minus I times r minus that term of loss through the internal resistance. And so in the end, the potential difference of the battery is what we can really use, and the EMF is what theoretically the battery can provide. But really, we are losing something inside the battery. Okay, I hope this helps.